Hey guys, yeah, I have some pretty sad news. So, I recorded this, but then when I finished recording, it turns out that the audio didn't work, so it was just a blank video. So hopefully this is my second time and last time recording this. And the main reason why I'm making this video is because some of you guys were asking on Slido more help on the precipitation reactions that form solids. So that's why I'm making this video. It's probably gonna be on. It's obviously gonna be on Discord. It's gonna be on the questions. So if you're watching this, you're probably on the Discord already. So let's read the slide. Precipitation reactions form solids. And here's the definition of a precipitation reaction. It says two ionic compounds react to form an insoluble product, which is known as a precipitate. So let's dissect this sentence one by one. Two ionic compounds react, and that's what we see right here. We have two different ionic compounds. If you remember, an ionic compound is a metal and a non-metal. So we have our metal, silver, and our non-metal, which is nitrate. Here's our second ionic compound. We have sodium, and we have our non-metal, chromate. And those are our two ionic compounds. So what's so special about them? The two ionic compounds, they're gonna react to form an insoluble product. The insoluble product has a name. It's called a precipitate. You know you're looking at a precipitate when you see a compound that is a solid. If it has that S, it's the species means that it's a solid. Notice how these have aqueous. They're aqueous because they're soluble in water. How do you know if you're soluble in how do you know if something is soluble in water? Well, what's important about precipitation reactions is that you're gonna need three things to solve these problems. What you're gonna need is your solubility chart. You wanna know what's soluble. You wanna know what's insoluble. You're really gonna need this. So make sure you have it. And you're gonna need your common polyatomic ion chart. If you don't have this, it's on the chapter 3 slides. It's on slide 11. And you're gonna need your other charge sheet. You're gonna need these charge sheets because you're gonna need to build your molecule. You're gonna need to build your compounds with the charges. And I'll show you what that means right now. Right here you have three different equations you need for precipitation reactions. You have your molecular equation, and you have your total ionic equation, and you also have your net ionic equation. That sounds like a bunch of words, which it pretty much is. And I'm going to show you how to solve one. So let's focus on the molecular equation. The molecular equation is just your standard, it shows everything. It shows what mixes with what species is which, and what does what. So let's replicate it. Right now, you're looking at a puzzle that's already been done. But like as a student, you want to know how to do this. And so that's what we're going to do. We're going to build this from scratch. So let's say you have a question that says silver nitrate and sodium chromate are added in water. So let's do that. I hope that background noise isn't getting picked up. If it is, it is what it is. I hope I'm louder than it. So, silver nitrate. By now, you guys should know that silver is Ag. Let me fix that. Silver is Ag. What about nitrate? I don't blame you if you don't know what that is. So let's consult our polyatomic ion chart. What is nitrate? Well, nitrate is right here. It's NO3 with a -1 charge. So we're just gonna leave it as AgNO3 because that's weird. My AirPod case. So we're just gonna leave it as AgNO3 because silver has a positive charge and nitrate has a negative charge. So negative and a positive one make 0. So the net charge is 0, so we're clear. The last thing we need to do is write the species. Is it going to be aqueous or is it going to be solid? How do I know which is which? How do I know if it's going to be aqueous or solid? In order to determine if a compound is going to have an aqueous or solid species, you're going to consult your solubility chart. So we're going to look for the rules for silver and the rules for nitrate. So let's consult. Let's see, let's look at our soluble chart. Right here, you can see right here, we see nitrate. Nitrate is soluble. But what about silver? I don't see silver on the solubility chart. So let's look at the insolubility chart. And it looks like silver is insoluble. It shows up twice. So silver is insoluble, but nitrate is insoluble. So what does that mean? If you have one element that is soluble, you're gonna write aqueous, even if the other one is insoluble. You're gonna write aqueous, even if one is soluble. So, positive sign, I'm adding these little underscores because we might need to balance it, just in case. You never know. So, we finished with silver nitrate. Now, let's work with sodium chromate. By now, you should know sodium is just Na. It's a group 1 element. But what is chromate? Let's check. It's probably a polyatomic ion. So let's check our polyatomic ion chart. Chromate, where is chromate? Oh, there it is. Cool. So chromate is chromium with 4 oxygens with a -2 charge. Oops. So let's put that together. However, before we determine our species, we have to check if the charge is 0, because if it's not 0, then we messed up. So, sodium has a positive charge, chromate has a -2 charge. They're not 0 because 1 minus 2 is -1, and -1 does not equal 0. So we need to fix this. Well, people get confused on how to make charge 0, and basically what I do is I cross multiply to make it balanced. So ignoring the charge, if it's positive or negative, we're just gonna put sodium with 2, and then chromium gets a 1. But you don't have to write the 1 unless you're a tryhard. But it's usually implied that there's a 1 right there if you don't write it. So we're gonna give this sodium a 2. Our final step, as always, is determining the species. So, let's check our solubility chart. Let's check the rules for sodium and chromate. So, oh look, sodium is the first thing you see on solubility. So, and it also shows up right here as a group 1. So, sodium is soluble. What about chromate? I didn't see chromate in the soluble, so let's check insoluble. There it is. Chromate is part of the insoluble list. But it's pretty interesting because chromate has an exception when it's attached to a group 1 or ammonium, and sodium is part of a group 1, so it's aqueous as well, even though it's insoluble, because it's an exception if it's attached to those 2 criteria. And chromate is attached to group 1, sodium, so they're both aqueous. And because they're both aqueous, because they're both soluble, we're gonna write aqueous. Okay, cool, we finished our reactant side. Now it's on to our products. How do we write our products? What do we do? Well, here's what we do. What I mainly do, how I solve these problems, is I look whatever was soluble. So we know nitrate and sodium are soluble. But why do they mix? That's because when they're trying to make a new ionic compound. We know that sodium is an ionic compound. We know sodium is a cation, and we know nitrate is an anion. So we're gonna put sodium and nitrate together. Remember, when you're naming ionic compounds, you put the cation first, the metal first. So subscript, just in case we need to balance this. We're gonna write sodium nitrate. The charges are equal because sodium has a positive charge and nitrate has a -1 charge, and they're gonna equal to 0. But what's the species? The species, we let's check. Sodium and nitrate. What is it tell us about sodium and nitrate? We know sodium is soluble and we know nitrate is soluble. So because both elements are soluble, the entire compound is going to be soluble. So when they're soluble, you write aqueous. Plus, what do we have left? So, because nitrate left, silver is all alone. It lost its anion. And what about chromium? What happened to chromium? Chromium lost its cation because it left it for a new person. And so let's bring them together, because a cation likes to bind to an anion, and silver is a metal and chromium is a non-metal. Silver is a cation, chromate is an anion. So we're gonna put them together. Let's do that. Ag, what is it again? Chromate, yes. But remember, we need to balance out the charges. And right now they're not balanced because silver is a positive 1 and chromate is a 2-. Right now the charge is -1, which is not equal to 0. So just cross multiply. And so you should get something like this. Ag2 chromium, because the charge is balanced out. So what's next? What species is this gonna be? Oh, whoops, messed up. So, silver, we said before that silver is insoluble, and chromium is insoluble unless it's attached to a group 1 or ammonium, and chromium is not attached to group 1 because silver is not a group 1 element, and neither is silver ammonium because silver is silver. So because when both elements are insoluble, we're gonna write solid as its species. So we're almost done with our molecular equation. We're almost done, except that we need to balance the equation because right now it's imbalanced. Because notice how we have one silver right here, but then over here on the product side there's 2 silvers. So we gotta fix that. So what I would do, in order to balance an equation, what I usually do is I look at which element shows up the most and save it for later. So oxygen shows up on all 4 of the compounds. So let's balance oxygen last. Let's focus on silver because that's what we have first. Silver has 1 right here and silver has 2 right there. What I'm thinking is to put a 2 to make it balanced. We have 2 on the reactants and we have 2 on the products. So silver is balanced. Embarrassing. How about sodium? Let's look at sodium. Oh yeah, here's sodium. Sodium has 2 on the reactants. Sodium has 1. So what I'm gonna do is add a 2. So now both sides have 2 sodiums. Okay, let's look at nitrogen. Is nitrogen balanced? Let's check. Right now, nitrogen has 2 on the reactant side. How about the product side? Nitrogen also has 2. So, nitrogen is balanced on both sides. What about oxygen? Oxygen, it's going to be 3 times 2, which is 6. Oxygen has 4 right here. So in total on the reactant side, there's going to be 10 oxygens. How about on the product side? There's 3, but 3 times 2 is 6. Right here, oxygen is 4. So 4 plus 6 is 10. So both sides have 10 oxygen atoms. So it's balanced in terms of oxygen. Chromium, there's 1 chromium on the reactants and there's 1 chromium on the products. So chromium is balanced, and because everything else is balanced, we're just going to add a 1. And that's basically how you find the molecular equation. That's literally it. I'm going to just label this as ME. Whoops. ME for molecular equation. That's basically how you find the molecular equation. That's basically how this happened. It's the same thing. That's all you have to do to solve the molecular equation. First, you look at each compound. You just balance out the charges and you determine the species. You determine the species by consulting your solubility chart, which you should have. You should always have it. And then you do the same thing for each compound. Check the charges, and determine the species. And then in order to, how do you get this? You just they just switch partners. So yeah, the cation's gonna find a new anion, and then anion's gonna find a new cation. That's all that's literally happening. And then you balance out the charges, you determine the species by checking your solubility chart. That's literally it. It's just 3 steps with a molecular equation. So, what about the total ionic region? It looks pretty janky. There's so much stuff going on, so much noise. I had to zoom out just to see the entire thing. It looks scary, but trust me, it's not. It's really simple. This is the easiest one, in my opinion. So, in order to find the total ionic equation, it's called total ionic equation because the name speaks for itself. It's the total ions in the equation. You're just looking for the total ions. But how do I know which one's an ion? You know you're looking at an ion when the compound says AQ, which is aqueous. That's how you know you're looking at an ion. They separate because they're soluble. Because they have aqueous. That's solid. It's not going to separate because it's a solid. They're not anions. So let's show you why this happened. Why does that look like this? Why is it so huge? I'm going to show you why. So in order to write the total ionic equation, you're going to do this. Whoops. So this coefficient is going to distribute to the silver and it's going to distribute to the nitrate. What does that mean? It's going to do this. So basically what you do, you're going to write 2 silver and its charge. After you write its charge, you're going to write the state it was in. Aqueous. Why is it aqueous? Because the compound it was originally found in was aqueous. You're going to do the same thing with nitrate. 2 because the 2 distributes. NO3 negative. It's negative because nitrate has a -1 charge. What's the species? It's going to be aqueous because it was found in an aqueous solution. Pretty easy, right? Now you're going to do the same thing for sodium chromate. Also, watch this. Pay attention to this. This, you see how sodium has a 2? Subscripts are going to become coefficients. So you're not going to write 1 sodium. You're going to write 2 sodium positive side. Why a positive side? Because sodium has a +1 charge. Why aqueous? Because it was part of an aqueous compound. Now, let's do chromate. I'm going to ask you something. Which one is the correct one? Is it this one or is it this one? It's going to be the top one. Because even though I said subscripts become coefficients, that only implies monatomic, mono, 1. So only one element does that. If it's just one element, it only does that. Polyatomic ions don't do that. Because this 4 belongs to the oxygen. it doesn't belong to the chromium. You can put coefficients. I mean, you couldn't put subscripts as coefficients on polyatomic ions, only if it looks like this. Only if there's parentheses around it. Then, when you write the total ionic equation, it's gonna look like this. Only if there's a 2 outside, surrounded by parentheses. So, species solid or aqueous? Aqueous, because it was originally found in an aqueous compound. Cool. And now, what we do next, the heck? My iPad froze. I don't want to record this again. Okay, we're back. Don't worry. Oh, okay. Now this is where we finished our reactant side. Now we're gonna go to our product side. So, what's left? What is that? Something's weird. My pen isn't writing words. Oh, it's moving though. Sorry, guys. Okay, we're back. Okay, so now we're gonna write the product side. So, remember, coefficients are gonna distribute. So, 2 is gonna go to sodium, 2 is gonna go to nitrate. So, it's gonna be 2 sodium. Is it gonna be aqueous or is it gonna be solid? It's gonna be aqueous because it was found in an aqueous compound. Next, 2 nitrate. Why a negative charge? Because nitrate has a negative charge. Aqueous, why? Because it was found in an aqueous solution. All that's left is our silver chromate. Here's my question. Are we going to separate it or are we going to keep it together? We're going to keep it together because it's solid. It doesn't have AQ. You only separate it if it has AQ because that means ions were possible. But ions are not possible because both of these elements are insoluble. So they stay together. So you just literally write it as it is. That's a lot of writing. And then write the species, solid. And that's basically how you do your total ionic equation. That's literally it. Total ionic equation. I just wrote Thai because I don't want to write all that. Yeah. So we finished our molecular equation and we finished our total ionic equation. All that's left is our net ionic equation. You're probably wondering, how did it go from something so big to something so small? It's pretty simple. The things that don't show up at the net ionic equation are called spectator ions. Spectator ions are ions that show up on both the product side and both the reactant side. So let me give you an example of what that means. Let's look at silver. 2 silver, positive charge. It exists on the reactant side as itself. Is it gonna exist as itself in the product side? Let's check. I'm gonna write this arrow to signal the separation of reactants and products. So let's look for 2 silver positive. It looks like 2 silver positive doesn't show up on the reactant side. So we're gonna spare him. How about 2 nitrate? 2 nitrate shows up on the reactant side. Is 2 nitrate negative charge going to show up as itself on the product side? Yes, it shows up right there. So what does that mean? It means we're going to cancel it out. How about 2 sodium positive charge? It exists on the reactant side. Is it gonna exist on the product side? And it looks like it does. It exists on both products and both reactants. So we're gonna cancel it out. Notice how you don't see 2 nitrate and 2 sodium on the net ionic equation? Because it's the net. Net means total. We cancel them out because they existed on both sides because they're spectator ions. I mentioned the word spectator ion, but what does that mean? Spectator ions are ions that don't participate in the chemical reaction. They're just watching. They're like nosy neighbors watching other neighbors fight. The people that are doing chemistry are the silver and the chromate. They're going to react to make a precipitate, which is an insoluble product. You know it's insoluble because it has that solid symbol, solid species. And nitrate and sodium, they didn't really do anything, which is why they just exist as themselves on both sides of the equation. So that's basically what a spectator ion is. And so the survivors, silver, chromate, and silver chromate, they're going to show up as themselves because that's all that's left on the net ionic equation. So let's do it ourselves. 2 silver, let's check. Does it exist on the product side? It doesn't. 2 nitrate, it exists on the reactants. Does it exist on the products? Yes, so we're going to cancel that out. Cancel that out. How about 2 sodium, positive charge? It exists on the reactant. Is it going to exist on the product side? Let's check. It does. It's there. So whatever survives, whatever doesn't get crossed out, is going to make it to the last step. So we have 2 silver, positive charge. Don't forget the species. Plus, what else is not crossed out? Chromate. Chromate's not crossed out. So let's write that. Don't forget to write the charge and write the species. You'll get wrong marked on an online assignment or a test or exam. H2O. And then what's the only thing that's surviving? So it looks like only silver chromate survived. So let's write that. Don't forget the species. Solid. And so basically this is how you find your net ionic equation. I'm gonna write net ionic equation. So that's basically how you find your molecular equation, and this is how you find your total ionic equation, and this is how you find your net ionic equation. So that's basically it. I'll post another video of another example just in case you guys need more practice. But yeah, that's basically it. That's basically the whole gist of this slide of what's going on.